what's going to be new? So I thought maybe I'd just spend a few slides on that. So, and this actually relates very much to your center, which I think is exactly the right direction to go, because like if this stuff is going to have an impact, we're going to want it to be really small. Oh, the animation doesn't work here, but one thing that you know, a lot of frequency combs we can make them pretty small, and you could buy them, you know, kind of. We often talk about the volume as 1 liter. Okay, that's what, 1,000 cubic centimeters. It's, you know, a liter is pretty small, and you can make them to run off electrical powers. You know, maybe it's 10 watts if you really fully account for like wall plug efficiency, what you'd get out of the electrical circuit. But kind of a real promise of frequency combs, I think, is the ability to make them like we would make semiconductor integrated circuits. And so building devices that are smaller and smaller, more and more integrated, but holding the same functionality. So if you thought back to my earlier picture of this gap between electronics and optics, I mean, what would be really cool, and I think will really be impactful, is when we get to the point where we can, you know, the optics piece is just like a chip. Camille talked about this. Other people talked about this at the conference, this area of integrated photonics and how impactful that can be. And it's really hard. And it takes time, it takes money. It probably takes like still maybe a really killer application that's going to drive it, to really drive down the price. So anyway, I just wanted to show a few slides on things that we had done, or maybe other people are doing, to perhaps, you know, seed your imagination. So a few years ago, we worked. One nice thing in the U.S. funding is there's a few agencies. One agency, DARPA, the Defense Agency, the Defense Advanced Research Projects Agency, that they get an idea about a project and they put a lot of money on it, and you can assemble a good team, kind of like your teams are, and you can really go after something. So this was already now 7 years ago, but this group of researchers, we got together, and the vision was to make this optical frequency synthesizer on chip. So something that would have microcombs in it, have these lasers that we needed, have the kind of self-referencing, and would be able to produce, like, programmably, you tell me what optical frequency you want and we'll make it. And this was kind of our concept. We showed, this isn't operating here, the video isn't, but let me just show you some of the hardware. The vision was this, an AD9833. Does anyone know what that is? It's a little analog to digital ADC. Okay, and you can buy one of those for like $15 or $10. You know, you can program it. It says, I want this frequency out, right? And but that goes to whatever, 100 megahertz. I don't know, but it's definitely an RF frequency. So our team, and many of you know John Bowers, professor at University of Santa Barbara, UC Santa Barbara, expert in integration. So these were kind of very early, like almost, you know, rudimentary, a bit Rube Goldberg, honestly. But this is kind of what at that point it would take, is to have, you know, I think there's different microresonators on here. At that time, we had to have kind of a dual gear system. We had to have a lower repetition rate microcomb at 20 gigahertz, a high repetition rate comb at 1 terahertz, and try to, you know, get these gears to work together. That's what's shown here. These were lasers coming from off chip and fibers. There was photodetectors along here and the electrical signals coming out. And then, you know, it never fully worked. Okay, but John was a visionary, and John's like, we're going to put it together anyway, because he knew that pictures like this can be valuable. But the idea was we even had folks doing like the CMOS electronics that would control all that. So this is, you know, V2.0, V3.0 of this, we called it DODOS. It was direct on-chip digital optical synthesizer. Okay, you got to have a good acronym. So I think this was pretty cool, and it was fun working with these folks to do this. More recently, it's like you get a good group of people, so stick together. It pays off. You see a lot of the same universities there. We kind of flipped it around. So that first DODOS project was to start with microwaves and synthesize optical. We just this past year, we had a project where we would start with optical and synthesize microwaves and make really low noise microwaves. And so you see that I won't go through all the architecture, but just to give you a little bit of the flavor, again, microcombs on chip were involved. We had kind of a crazy idea, which, I think it worked out, but it's not perfect, is that we actually made for our reference a tiny little bulk Fabry-Perot cavity. It's not a spiral resonator on chip. So we kind of, DARPA liked that. There were other teams that were trying the spiral resonator on chip. We decided we're going to try and make this bulk cavity, but we could make an oscillator that made really low noise microwaves with that. And there's some pictures of the hardware. There's work around the community, people using frequency combs and for LiDAR. This is Kippenberg's group, taking a picture of a bullet or out of what is it? It's a pellet gun, right? It's like, that was a cool picture when I saw that. And he did it with this dual comb LiDAR type idea, right? And a lot of these experiments were not fully integrated. If you went into his lab, it was a tabletop thing. High-speed spectroscopy for different types of dynamic situations. I think it's a really great application. Some of these applications also don't need like the full self-referencing of combs. I think those are nice angles. Yeah, very high-speed communications, and I know your teams are experts in some of that. This was one that caught my attention just because I got to know Karen Bergman a little bit. Some of you probably know her, and this was work that just came out. I'm really excited about this. This just came out earlier this year, but some of you know this problem, could probably speak to it better than I could, that the current GPUs that you get from NVIDIA are so powerful, can process so much data that they actually have to derate them, turn down the clock rate, because if they run it at the full clock rate, they can't get the data. There's not enough wires. There's not enough high enough data transmission around the electrical processor to get the data out. So what her team has been working on, and I think there's probably others here who are doing it as well, is to try to bring microcombs right up to the chip, right? So you have the optics touching the CMOS electronics. And so the concept would be that you could take full advantage of the very high processing power, high processing speed, but you could get the information out. They call this, I hadn't been aware of this term, it's the escape like perimeter. It's almost like the information is trapped on the chip. You have to help it escape. Another thing I think that's really nice about this work, I think is really interesting, is the energy scaling. And, we all hear, and, I'm not an expert in this, so please correct me if I say something wrong, but we all, people are building data centers and AI, machines, lots of energy is needed, right? And so I think this is one thing that may stop the whole thing, is, right, if there's not enough energy to fuel these things. So optics and photonics could push the energy usage down. I don't know if it can push it down enough, but this is an area, for example, if frequency combs found a role here, I think it would be revolutionary. So I was inspired by her work, and probably some of you are already thinking along those lines. I'm not saying anything new, but anyway, yeah, combs for AI. There's kind of interesting combs. A comb that doesn't have an equal mode spacing. Now that's a mind bender, huh? We work really hard, but here you see that the frequencies, there's an n squared in there. So the comb teeth are closer here, but what if you could make them so they perfectly change quadratically with n, okay? this was Thomas Udom. And the idea there was that you could do some kind of interesting metrology with that. For example, with spectroscopic sensing, because the comb teeth here would have a certain heterodyne beat. At another place in the optical spectrum, they'd have a unique, different heterodyne beat. So you could measure things just with a simple comb, one comb. You wouldn't need two combs, as I talked about the other day. I think quantum frequency combs are quite interesting, and there's people call them combs, but they don't have this type of coherence, at least yet, that I talked about with combs. And these are usually OPOs or parametric oscillators that it might involve microcombs or microcomb hardware, but they usually run below threshold. So they make like correlated pairs of comb teeth, but they're vacuum states, right? They're entangled vacuum modes. And so how that's going to come out with combs, I'm not exactly sure, but there's a lot of really interesting work in that area as well. I mean, I think, if there really was going to be some sort of unique, these are cluster states, and this is Olivier Pfister at University of Virginia, as algorithms for using those for computing or for information processing. It certainly would be very compact if you could do that with microcombs. So who knows where it's going to go? Maybe probably the best idea is unknown. So I just end with my chart, maybe saying where are things going to go? I think this was my projections, right or wrong, but just something to talk about. I think combs at extreme wavelengths are interesting. Like, how do we get to X-rays? How do we go more to the infrared? I think infrared is very important. Combs in extreme environments, space. I think that'll be, you'd want things like microcombs there. Ubiquitous combs, I think that's the CMOS, integrated combs. So you could, right now, when I was talking with people earlier today, the Menlo comb, $1 million, right? For the rack version. Maybe you could get a slimmed down version for $100K or something. It's still a lot of money, right? And so what would drive the application that would push that so you could make them at volume and they really cost $1,000, right? Or a few $100s. Yeah, I already mentioned combs for data communication, quantum combs. I went to an interesting workshop a few months ago or a month ago on petahertz electronics, where people were talking about, well, we can control the carrier envelope phase very well. Can we drive electrical currents with that carrier envelope phase? Is there something interesting we can do, at petahertz rates? That one seems pretty far out, but that's why you get together and maybe dream about it a little bit. But yeah, probably the most interesting thing we wouldn't even know now. So I think I talked long enough. I'll stop there. Yeah, there's too many people to thank. I stole slides from other people and all that, but yeah, thank you for listening.